Hello everybody, welcome to another video talking about physics and the mathematics thereof. So this is just a follow-up video on the video that I made about deriving Newton's second law. There have been a lot of really fantastic questions and I want to make a couple follow-up videos, starting with the fast way to do things. The last video I used techniques that you would see at the beginning of an introductory quantum mechanics course. Now I'm going to be using Ehrenfest's theorem, which I have written down here. All we're doing is putting in the momentum operator for the operator A, and Newton's second law almost comes out. And that'll be the topic of the next video, the corrections to this result and the correspondence between quantum and classical mechanics. Without further ado, let's jump right in. If we put the momentum operator in here, then we are going to find that what we really need is the commutator, right here at this step, between the momentum operator and the Hamiltonian operator. Because this term right here, whoops, sorry, that should be a P, momentum, goes to zero. Because this is a partial derivative, the momentum operator does not explicitly depend on t, so this is going to go to zero. So that was relatively painless. Now, something else that's nice is the momentum operator shows up explicitly in the Hamiltonian. So this whole term right here is going to commute with the momentum operator, right? We'll get momentum cubed, and momentum cubed is momentum cubed. So this term doesn't matter. And really what it comes down to is just the commutator between the momentum operator and the potential energy operator. So if we write that out, what we really care about is this. Let's make a little aside. You'll have the momentum operator, the potential energy operator. And remember, when you're working with a commutator, you always want to make sure that you act on a test function, which you then throw away in the end. But it's not entirely obvious how the commutator is going to behave if you don't operate on a test function. Maybe you possess greater wisdom than I do, but I can't do this sort of operation without a test function. I have the momentum operator written down here, but remember that the potential energy operator is just multiplied by the potential energy. So if we operate this out, we can factor out, rather, the h bar over I. Here, we're going to have the product rule. So that's just going to be the partial of the potential with respect to x times our test function, plus the potential energy times the partial of our test function. And then over here, we have minus the partial of our test function. So these two terms are going to cancel each other out, and what we are left with is h bar over I times the partial of the potential energy with respect to space times our test function, and we throw away our test function and we find that the commutator of the momentum operator with the potential energy operator is simply h bar over I times the partial derivative of the potential energy with respect to space. So our little aside is over. If we plug that in up here, we are going to find that the time derivative of the expectation value of the momentum operator is equal to 1 over I h bar times the expectation value of this right here, h bar over I times the partial of the potential energy with respect to x. Now if we factor this out, the h bars are going to cancel, the I times I just becomes minus 1, and we get the expectation value of the potential energy as a function of position, and this will be important later with respect to position. This is often called an equation of motion when you have a total time derivative of something. And this looks suspiciously like Newton's second law, but we will discuss in the next video that there's a little bit more subtlety to it, and we'll explore that in full detail. I hope you found this interesting. I hope you'll check this out as well as my first video on this topic. You can compare and contrast. One method is a lot faster than the other. And I'll see you next time when we look at more of the details. Thanks for watching.